The traditional model of coagulation, called the cascade model, conceived of clotting as a series of steps. One protein reaction activates another. The cascade follows the intrinsic or extrinsic routes that converge into a common thrombin-mediated pathway. While the cascade theory provided a useful model in vitro, it did not provide an adequate explanation of hemostasis in the clinical setting. Recent clinical data suggest that properties of cells have a role in controlling coagulation. The surface of activated platelets appears to be an important site for the thrombin generation necessary for clot formation. In this cell-based model of coagulation, there are three overlapping phases. The first phase, initiation, takes place on the tissue factor-bearing cell. An injury to the vessel wall exposes tissue factor, which has a high affinity for factor 7A. Factor 7A binds with tissue factor to form a complex that converts factor 10 to factor 10A. While this may not be sufficient to sustain hemostasis, this small amount of thrombin can initiate coagulation. In the second phase, amplification, thrombin moves to the platelet surface, activating the platelets as well as factor 10 and promoting aggregation of platelets at the site of injury. The coagulation response is amplified as platelets adhere, become activated, and accumulate activated cofactors on their surfaces. In the third phase, propagation, active proteases interact with their cofactors on the platelet surface. Activation of factor 10 produces a burst of thrombin, a critical step in the clotting process. Thrombin converts soluble fibrinogen into an insoluble fibrin clot. This thrombin burst promotes the creation of a stabilized solid fibrin plug. This cell-based model of coagulation not only explains normal hemostasis, it also explains the mechanism underlying hemophilia,